successfully found today what we call the common solution for a system of linear equations in two variables. We have two different variables, x and y. So in order to solve a system with two variables, you need two equations. Okay, so in the first part of this, I gave you a point and asked you if it satisfied two different equations, and you found that it did. And so therefore we can call that the common solution to the linear system. Then I asked you to graph two lines, and we discussed the different ways of graphing them. And you saw that this idea of the common solution visually was what when you graphed the two lines? What was it visually, the common solution? How did you find it visually? What was that 4, -1 as a visual once you graphed both lines? The intersection point, right? It's what they had in common, right? That's what intersection is about, when you intersect two sets. So basically what you're doing here is each line has a solution set that has an infinite number of points in it. And what you're doing is you're finding that one point where they intersect, with the one point that both sets have in common. Okay, so it's a really nice method for finding that intersection. So we did it visually, or what we say graphically, and what we're going to do today is we're going to do a similar problem, but I have it already graphed for you, as you can see in this graph here. And what we're going to do is look at how would I find that algebraically. Okay, there's an algebraic method, and the reason why we want an algebraic method is hopefully it takes less time, and if our answer was really funky, like it had fractions, right, we wouldn't be able to get a really good estimate if it was a fraction. So you want to start us off, Di, with reading this systems of linear equations in two variables? We're pretty much okay. The last problem on the preview exercise, number 3, was a single equation which we could solve because it had one variable. No problem. If you have one variable, one equation, you can go to town, right? Now we have two variables, so to find the common solution, you need to have two equations. Okay, so this graph below can be represented or modeled by these two different equations. The red line is the model for the equation x plus 2y equals 142. This represents the percentage of people in the United States that are married years after 1970. So if we were looking right here at this point, that would be roughly 1990, there was roughly 60% of the US adult population was married. And as we can see, it's steadily declining as the decades are going on. And so if that's declining, then the percentage of never married people must be increasing. And this is the equation of the line that models this. That models this phenomenon of the increase of never married US adults. So what we can do visually is we can estimate that intersection point, which is the solution, the common solution to both of these, because it doesn't fall in a spot where we can say what it is exactly. So all we can do visually is estimate it. Someone want to give me what they think is the estimated intersection? Amber? 69,38. So we're saying 6938 is a really good, because potentially that looks pretty darn good, close to me, of what would be the common solution. But we really don't know if it's 69 or 68 point something, and we don't know if it's 38 or 38 point something or 37 point something. So to really find the exact solution versus an estimate, that's where the algebra comes in. So what does this intersection point tell us? Be sure to describe both variables being graphed by using appropriate numbers and units. So any given story like this will have two coordinates, and to help you write the sentence about what this means, put in the units right beside the coordinate. For example, 69 is 69 years after 1970. So put it right in there to help you out with your sentence or your interpretation. After 1970. And the 38 represents the percentage of US adults. So once you put in your units along with your coordinates, then you can write your sentence from there. Does anybody want to give me a shot at what you, take a shot at what you think would be a sentence that would give you the meaning for that intersection point? Not at it. Tony's being brave. Okay, go ahead, Tony. What year is that? Let's be specific. 2000, yeah, in the year 2520. No, that's way too old. In 2039, yep.
When the percentage of adults are equal, are married is equal to the percent. I don't know.
All right. So in the year 2039, the percent of never married US adults equals the percent of married, which is what percent? Which is 38%. So you always want to be able to see each of your numbers and its units in your sentence. Right, that's exactly what it means. So someone in my other class said, well, if 38% are never married and 38% are married, that's only 76%. Where's the other 24%? So we started talking about what would be other possibilities? What you say, Di? Divorced, right? Or someone said someone might be on their knees proposing, right? So they're just not in either of these categories yet. Okay. Too expensive to get married. Yeah. Okay. All right. So again, this divorce is more expensive. That's true. So maybe that's why people aren't getting married. Okay. So what we have now is this linear system right here. Here's our system that we just graphed and looked at the intersection point. We got an estimate, but now we want to look at two algebraic ways quickly. I think this should be a review for just about everybody who's taken Math 096 recently. This should be a pretty quick review, okay? So x plus 2y equals 142 and negative 3x plus 10y equals 160. So let's take a look at what this looks like algebraically to find the solution. One method is called substitution, and the idea behind substitution is you solve for one of your variables in terms of the other. That's the language we use. For one of your variables in terms of the other. Okay, so we have these two equations, x plus 2y equals 142, negative 3x plus 10y equals 160. Okay, so the idea here is, can you solve for one of these variables easily in terms of one or the other? The first one. Why? Why'd you say the first one, Fabian? Yeah, so the key here, what you want to look for, right, is you want to look for a variable that has 1 as the coefficient. Nick, I gave you this packet the one time you came at the end of class, your lecture notes. We're on class 7. So this is your first official class today. We'll have to talk at the end of class, please. A variable with coefficient of 1. And notice right here, you have that variable. That's why Fabian picked on that. So over here, he just sort of pulled this aside and says, hey, this is going to be really easy to solve for in terms of y. I'm going to just solve this equation for x. I don't have to do any other manipulation because it's already set up. It's setting itself up. So we get x equals 142 minus 2y. Does everybody see how I got that? So you're working ahead there, Tony, and getting the answers all set for me? Good. All right. So now instead of seeing this equation, you could literally just erase it from the face of the earth and put in this equation. X equals 142 minus 2y. They're the same exact equation. Now look at how beautiful that is, because now you can say, hey, my second equation here, which is one equation with two unknowns, which I can't do anything with other than graph it, I can now make it into one variable by using this information right here. It says x is always going to be 142 minus 2y. So where you see x in the second equation, you can substitute now what it represents, 142 minus 2y. So we get negative 3x, whoops, not 3x, it's negative 3 times x, and what are we calling x? Right, 142 minus 2y plus 10y equals 160. Right? And now we use our distributive property here, and help me just in case I make a silly mistake. We combine like terms. So if at any point, I'm making some assumptions here because we're in Math 107 now, but if at any point you don't see how I get from one equation to the next, just stop me. Say, Linda, hang on, I don't know what you're doing. All right? And so we get 16y on this side, and what do we get over here? 586. And when we divide both sides by 16, Tony, what do we get? I thought, oh, he did, okay. What? 36.625, which is the same thing as 36 and 5/8 if you have it as a fraction. All right, so what was the estimate that we got when someone gave us an estimate? 38? So pretty close. That estimate was pretty good. Are we done with this problem? Have I found my common solution? Why not? Ashlyn, do you have a question? Yeah. Sure. Yeah. I don't have a preference. But what I do have a preference for is, never mind, I'll tell you later. Okay, because I don't want to get anybody confused. Both of these are equivalent, so however you write it is fine with me. So are we done? Have we gotten our answer? Why not, Di? Oh, because I didn't say so, I'm asking a question. Taylor? I still need to find x, because remember, I'm trying to find a common solution, which is a point on a graph which has both an x value and a y value. So now you always go back to one of the original equations, never an equation that you've played around with, because if you made a mistake in creating that equation, you're just going to perpetuate the mistake. It's just going to carry forward. So go back to one of your earlier equations. I'm going to pick on x plus 2y equals 142 because the numbers are smaller and my head can't handle anything quite too big. And I'm going to put in 36.625 for y. So I put in 36.625 for y. And now I'm going to solve this for x. And what does x come out to be? For those of you who have eager beavers and you've worked ahead. 68.75, right? Okay. So the common solution is x is 68.75 years after 1970, and roughly 36.625% of the population will either have never married or will be married. And if you're really curious, you can always see if this is the right solution by placing it into your second equation. And once you do that, 160 should equal 160. And if it doesn't, it means somewhere along the way you made like either an algebra mistake or adding and subtracting or division. So you should always check your work. Okay, so that's the substitution method. Let's quickly look now. I'm going to ask you to tell me this system again, because I'm going to put in a new page here. So the first one was x plus 2y 140 and negative
142.
Okay, 142 and negative 3x plus 10y was 160. Okay, now notice every time you have a system, you always sort of put it together with this half a brace, okay, on the side. That indicates it's a system and you're looking for this intersection point or this common solution. So the addition method says, what if I add both sides together? That's legal. I can add both sides together. Let's see what it gives me. I'm going to use exactly what it says. I'm going to add the left sides and the right side. So I get negative 2x plus 12y equals 302. Yeah, I can't solve that for an 1x and 1y because it's one equation with two variables. I can get a line from that for sure, but it's not going to tell me what that common solution is. So in this case, adding it up didn't help me because I wanted to get rid of one of those variables. I wanted to eliminate it by adding the two sides. So I'm back to the drawing board here. I still want to use this idea of adding both sides, but what I have to think about and what I have to see as most convenient is, can I make the coefficient, which is the number multiplying either x or y, the opposite of the coefficient in the equation below it? So when I add them, what's going to happen? They'll cancel, they'll become zero because they're going to be opposites. So you can pick on either the x or the y, but since x already has a number that's negative, has a negative coefficient in the second equation and a positive coefficient here, then I might as well just multiply this top equation through by the opposite of negative 3, which is plus 3. So I'm going to multiply this by 3 and this by 3 and that by 3. So now this is my system. This equation is totally equivalent to the original equation that was there. So my purple equation is the one that I've manipulated. And now I'm going to add both sides, okay? And what happens is this becomes a big hunky 0x, and 0x is a nice big 0. And now I have 16y equals 586, which is exactly what I ended up with before. And when I divide both sides by 16, what did I get again? 0.625. And again, you go back and substitute. You find x by putting this in for y and solving the equation. So two different methods. They both lead you to exactly, what was it again, the percentage, 38.75? Yep, thank you. Oh, 68.75, thanks. Okay, so those are the two methods. It's a quick review, I realize, but the reason why we did this review for you is because one of the story opportunities that you all did on Wednesday lends itself beautifully. All of these investment problems that you did them with one unknown. And using this total here, like for this money invested in the scholarship, using that to create an expression for your other unknown amount of money. So today, now that we know how to work with two variables, we're going to try to make life a little easier. This is like the type of thing that we can now do because we know how to solve two equations with two unknowns. So now, notice how I've set up this table. We're talking about investing money. So my first column here is the amount of money I've invested. And I'm just going to throw my unit on there because we talked about yesterday, Wednesday, writing out what our variable means, which means we can either write it out by hand or we can create this table. But this table should include exactly the same thing in it that I've asked you to write out by hand. So let's X equal the amount of money invested. And let's say it's going to be the amount of money invested where? At the lower rate. So notice I had to put in a row here that represents everything that's going to be done at the lower rate. So I'm calling X the amount of money I invest at the lower rate. And now I don't have to say 10,000 minus X like we did on Wednesday for the amount invested at the higher rate. I can just call it Y, the amount of money invested at the higher rate. Or I can continue like I did on Wednesday, just defining everything, or I can use this little table. Now, if I'm lucky, looking at my columns, now this last row here is either the total or a relationship, because you don't always know the total. Sometimes you're told what one account has so much more than the other, so you don't always come out with the total, but you have a relationship. Do we happen to know the total of the amount of money invested at the lower rate and the higher rate? 10,000. So guess what? You put a little plus here, and there's your first what equals what. There's your first equation for your system. It's going to just fall right out of this table. It's going to be beautiful. Now, not all of these problems you do, you need a table for. This do an investment type of problem sets itself up beautifully for this, but not all of them you need. So don't go looking for a table for every single problem you see. It's just a tool for this type of problem. Now, we know the percent interest for the lower rate was what, 4%? That's 0.04. And the higher rate was 8%. Now, the amount of interest earned in each account. So if we were writing this out on Wednesday, we would say 0.04 times X. In other words, I just multiply straight across. And that tells me the amount of interest earned in dollars on X dollars. And when I multiply straight across here and get 0.08y, 0.08y tells me the amount of interest earned in dollars on X dollars. I mean Y dollars. Okay, I guess I can just say Y dollars and then the units there. I don't have to say it twice. So now I have my amount of interest that I've earned represented. Now, do I know the total interest earned, or do I have a relationship between the interest in this account and the interest in that account? What am I told in my story? Yeah, expect a return of interest of 550. That's a total. So, wow, you mean I get two equations right away? How cool is that? And I get 0.04x plus 0.08y equals 550. Okay. Now I have my system. And now to solve this problem, I use either substitution or I use addition. So let's just take a look at substitution. If you look at this first equation, does it set itself up really nicely for a substitution? Yeah, and if you solve for y here, look what happens. You get 10,000 minus x, which is all the work you did on Wednesday. The total, take away the amount of money invested in the other account. So now all you do is you pop that in there and you solve for y and you go back and get x. You can finish that on your own. I'm not that interested at this point in you finding the answer. I just wanted you to see the process. So you can finish this on your own, and then you have a series of class activities. You have about 35 minutes or so to get those done. Use your flags if you have any questions, and I'll be glad to help you out.